So essentially, this is what you should be looking at whenever you get done with number 13. The last video got cut off a little bit, so if you had somewhere where you had a mass between 120 and 160, those would also be acceptable, as long as it is bigger than the selenium, and the selenium is 79. So if you saw a pattern 16 to 32, that doubled. 32 to 79, that kind of doubled, that just over doubled. And that also had 6 valence electrons. So this next part, I have a correction for you to make. So I'm going to take that one. We've got a new page here. Unfortunately, I didn't have you fix this until now, so I apologize for that. So on aluminum, please cross off aluminum and change aluminum to gallium. I should have said gallium and not aluminum. Huge, yeah, very sorry about that. So really quickly, before we get started, one thing you certainly need to have in front of you, if you already tried to do this problem with knowing that that was aluminum, I apologize, it should be gallium. So here, you're going to be needing your lab that we did last week, the demo lab, where you're comparing calcium, magnesium, and aluminum. So one of the first things you need to do is kind of see the pattern as you're going down a group and when you're going across a period. Excuse me, I got my little book situation there. So this is looking at our data. Notice that this is a reaction with hydrochloric acid, so we're really only looking at temperature. So here is calcium and magnesium, and I'm going to show you those on the periodic table. Here we've got calcium and magnesium. So going down a group, we got magnesium and calcium. Those two, calcium is bigger than magnesium. So it's essentially, so this one, it bubbled a lot. This one, it bubbled a lot and it got warm. This one, it got bubbled a little. There's no reaction seen here. So following that same pattern, we got magnesium and calcium. Those are in the same group. So strontium is also in the same group. But strontium is then below calcium, knowing that the pattern goes, here we have reactive, here we have pretty reactive, and as we go down, it's going to get more reactive. So we've got strontium. Strontium, a prediction, an observation would be bubbled vigorously. And we're going to say our initial temperature, because it's room temperature, all of these, we can make a prediction that the prediction would be 25 degrees Celsius for each one of these hydrochloric acids before we drop essentially this middle in. So then compared to strontium, calcium is going to bubbles a bit, or bubbles a lot, but vigorously is considered to be way more change in temperature than calcium. And then gallium is, so when we were looking at these two, notice that between magnesium and aluminum, both of those are in the same period. So as we've got, we've got magnesium and we've got aluminum, as we go across the table, that becomes less reactive, looking back to our data. So we've got magnesium and aluminum. So this one, magnesium and aluminum, magnesium was quite a bit more change in temperature as this one. This one changed 25 degrees Celsius, this one only changed 7. So this was aluminum was significantly less reactive. Gallium, on the other hand, not aluminum, gallium is also going to have the same. So here we have calcium on this side and gallium over here. Same idea, same pattern. So calcium is going to be more reactive than gallium. So this one, your prediction would be very slow reaction. So knowing that information and knowing as you go down, this right here would be going down a group. As we go strontium to calcium, and here calcium to gallium, we'd be going across a period. So here, as long as your number is bigger than these ones, so we'd say 25 degrees, maybe this one went up to 100 degrees Celsius, so then that was a change in temperature of 75 degrees. And you could say that this one was a change of temperature of 25 degrees Celsius. And then this one, maybe just say you could, gallium, maybe you made a prediction that it would only changed 5 degrees Celsius. As long as your pattern is that you have a change in temperature, so this one would be a change of temperature of 75 degrees, this one would be a change of temperature of 25 degrees, and this would only be a change in temperature of 5 degrees. That's essentially kind of getting this table. Go ahead and look onto the next video. Actually, no, I'm not going to go on to the next video. I will continue on with this one. If it gets cut off, then I will continue on. So number 14, it says, based on the evidence you saw in the periodic properties of metals lab, which essentially was these ones, what is the trend of the reactivity as you go down the group? What specific evidence do you have to back up your claim? So this is really when, instead of using the predictions from the previous table, you are using this information from this lab. So as you go down a group, the reactivity increases. The evidence is that calcium reacted more than magnesium. And when we compared so looking again back to this, when we compared the reactivity of magnesium and aluminum, what trend of reactivity of metals as you go left to right? So we determined that also in the predictions. I think that I could have placed the table that is right before 14, 15, and 16 towards the end of this, but I chose to do it towards the beginning, so I tackled it in the beginning of this video, kind of front-loaded it for you. So here we have, as you go down, across a period, left to right, the reactivity decreases. And what evidence do we have? That aluminum reacted less than magnesium. And then number 16, what does the effective nuclear charge have to do with the trend in reactivity going down a group of metals? So here we have the lithium, sodium, and potassium as our example. Use a diagram to the left to explain your answer. Use the following terms: effective nuclear charge and the valence electron. So this is kind of going for the 4. You'll need to also include giving some information about ionization energy, electronegativity, or atomic size to go for the 4 on the assessment. But this is kind of getting you to the spot about effective nuclear charge. As a reminder, what is effective nuclear charge? I'm going to kind of write down what we've written in our notes. So the effective nuclear charge, I'm going to, because my little setup here is in the way, I'm going to kind of shrink the amount how I'm writing. The effective nuclear charge decreases as you go down a group. As a reminder, the effective nuclear charge is essentially the pull from the nucleus on the valence electron. So I'm going to write the short. The valence electron is not held as tightly. Let me move this up a little bit. Not held as tightly on potassium which is K, as on lithium. So therefore, the valence electron of potassium will, it doesn't really fly off, but it will fly off or react more easily with other substances than lithium. So saying that the valence electron is not held as tightly on potassium as on lithium. The valence electron of potassium will fly off or react more easily with other substances. I'm going to take off than lithium. That might make it look a little more confusing. So it will react more easily with other substances. So saying that compared to lithium. So that valence electron here is being held a lot tighter here than it is here. So that's the gist of the last part. That's to go for a 3 on the assessment. There'll be a check for understanding next class. So we are actually going to postpone our assessment by 1 day, and you'll have 1 extra day to kind of get some of this information, make sure that you're prepared for the assessment. I hope you have enjoyed your time, and take care. Feel free to email me. Remember, my email is mday@pps.net, or you can schedule an office hours with me via the remind.com app.